introduce our second speaker for this session. As you can see, Tony Guttmann, and he'll talk on Rodney's 398th solution of the Ising model. Thanks, Tony.
Thanks, Murray, and thank you for the opportunity to contribute on this very sad but very exciting occasion. I should perhaps say that before I actually start talking about this topic, the only paper I wrote with Rodney was on directed percolation, where he wrote to me and said that he was interested in my work on directed percolation and discovered that he could set up a transfer matrix formalism for the directed percolation problem on the square lattice, which was related to the Ising model, but with 1, 2, and 3 spin interactions. And was I interested in collaborating with that? And I said, very much so. And as a consequence of that formulation, Rodney was able to set up some transfer matrices, which I then programmed, and we extended the existing power series expansion for the percolation probability from 8 terms to 41 terms, which gave us a series that was long enough to get very accurate estimates of the critical percolation probability and the critical exponent. And one of the interesting aspects of that calculation is that while we only got 29 terms of the series expansion directly from the transfer matrices, because we were working on this finite lattice, Rodney realized that the errors in the subsequent terms could be expressed as linear combinations of Catalan numbers. And of course, Catalan numbers are bread and butter to the combinatorics community. And Xavier Vianot in France discovered this paper and was very excited by the occurrence of Catalan numbers and gave our paper to Mireille Bousquet-Melou, who was his PhD student at the time, and she proved the results that we'd conjectured. I mean, we were more interested in getting the actual series data rather than proving that these corrections were correct, but she did prove that these were correct as part of her thesis, and this got her interested in problems or combinatorial problems in mathematical physics, an interest that has persisted to this day to the benefit of the field. So once again, this is probably an influence that Rodney was unaware that he had, but one that has paid considerable dividends. But I want to talk now about some other work of Rodney's that had significant influence on my own work, which was trying to solve various polygon models. And I was influenced in that by Rodney's work on the Ising model based on observations of symmetries. So symmetries, as everyone knows, are among the most important guiding principles in both mathematics and physics, and often a problem can be solved by symmetry considerations alone, or even if not solved, symmetry considerations can often greatly reduce the work needed to find the solution. So here we're going to consider a type of symmetry known as self-reciprocity in mathematics, or as inversion relations in physics. The first use of inversion relations that I can find in statistical mechanics was the solution by Stroganoff in '79 of several 16 and 81 vertex models. In that work, he considered a finite toroidal lattice of n rows and m columns, each bond of which is colored by one of R colors. And then in terms of the transfer matrix, T subscript m, the partition function is, as usual, given by the trace of the transfer matrix raised to the power n, where that transfer matrix is an R to the m by R to the m matrix, whose ijth entry is the contribution of a single row of m sites connected to the row below by a set of vertical bonds in configuration I, and to the row above by a set of vertical bonds in configurations J. It depends on the temperature T and on the R to the fourth parameters specifying the vertex energies. In the thermodynamic limit, the partition function per site is given as usual by the limit as m and n go to infinity of z to the 1 over mn, and this is given as the limiting value of the trace of the largest eigenvalue at which we assume to be non-degenerate. For simplicity, we'll consider models or a family of models whose vertex energies are functions of a single parameter b. The models solved by Stroganoff are integrable by virtue of the commutativity of the transfer matrices at different values of this parameter. The B dependence is only in the eigenvalues, so that's why B is often called the spectral parameter. And the key observation is that the inverse of the transfer matrix in these models is itself a member of the commuting family up to a scale factor, psi. And if we now let both sides of equation 3 act on the eigenvector corresponding to the largest eigenvalue, we obtain the functional equation shown as equation 4 there. And then the commutativity of the transfer matrices for all values of B allows for the analytical continuation of the function kappa from B to psi of B. Now, if we know psi and phi and use the analyticity of kappa, Stroganoff found a unique solution, thereby reproducing Rodney Baxter's results for the symmetric 8-vertex model and the homogeneous ferroelectric models, and in addition, obtained results for a certain 81-vertex model. So next, I want to review Baxter's derivation of Onsaga's expression for the partition function of the two-dimensional zero-field Ising model that relies only on symmetry arguments. We're drawing the square lattice at 45 degrees to the horizontal and letting the nearest neighbor couplings along the two lattice directions be denoted J and J primed, and we define low temperature variables X and Y as e to the minus 2 kappa and e to the minus 2 kappa primed with, e to the minus 2k and e to the minus 2k primed with k and k primed, defined as usual as J over kt. The transfer matrices for different choices of parameters will commute, provided they have the same value of this elliptic function, elliptic parameter k, which is the reciprocal of sinh 2k, sinh 2k prime. The key observation is that the transformation which inverts the transfer matrix is the transformation from k to k plus I pi on 2, where k and k prime to minus k prime. And that transformation doesn't modify the value of k. If we define the reduced partition function by just extracting this initial multiplying parameter e to the minus k prime from the partition function kappa, then the reduced partition function lambda obeys this elegant looking inversion. Sorry, I've forgotten to advance the slide. I beg your pardon, yeah, we're up to here. The reduced partition function per site is given by this, where this reduced partition function obeys the inversion relation lambda xy, lambda minus x 1 over y is 1 minus x squared. And of course, by symmetry, we have that lambda xy is equal to lambda yx. So we have these two relations, the inversion relation and the symmetry relation. And then if we inspect the nature of the low temperature expansion, it leads us to this conjecture, which is readily proved from the Onsaga solution, that we can write this reduced partition function in this way, where P is a polynomial of degree 2m minus 1 in y squared, and the denominator takes this particularly simple form 1 minus y squared to the 2m minus 1. The fact that the coefficient of x to the 2m is a rational function of y squared follows readily from the nature of the low temperature expansion, but the fact that the denominator has this really simple form is far from obvious. But Baxter showed that the inversion relation and the symmetry relation that we had on the previous slide, plus the form of this denominator, is sufficient to determine lambda completely. That is to say, we can calculate these numerator polynomials one by one for increasing values of m. The way this works is that the symmetry relation reduces the 2n minus 1 unknowns to n, and the inversion relation allows us to find these particular nodes. I was able to show quite straightforwardly that you could solve for the spontaneous magnetization in exactly the same way, just from symmetry arguments. Interestingly, if you try and apply similar arguments to the susceptibility, the anisotropic generating function has denominator zeros that aren't just the simple roots of unity, but they are steadily higher order roots of unity, so that in the unit circle of the complex plane, you eventually get a natural boundary, which is enough to prove that the susceptibility is not differentially finite, or as is the free energy. So that observation led to the conjecture that solvable models should have anisotropic generating functions with denominators with zeros only at z equals 1 or z equals plus or minus 1. And this was subsequently tested by Tsukuhara and Inami, who thought that just about the hardest solvable model we have is Baxter's solution of the 8 vertical. So they took that as a test case and found that this too could be solved by these same arguments, and that the denominator zeros in the anisotropic generating function for the partition function all occurred at z equals 1. We've been assuming in the problems that we've looked at, well, at least the Ising model, that we've been assuming integrability and that the transfer matrix and its inverse are both members of some one parameter commuting family. But what about models for which this property doesn't hold? Then in that case, it's still possible in some cases to obtain an inversion relation, either by a direct analysis of the low temperature expansion of the partition function to some finite order or some other methods. So for example, Jean-Marie and Jekyll showed that the logarithm of the partition function of the Q-state Potts model satisfies this inversion relation, shown here as equation number 11, which of course reduces to the much simpler Ising model relation when we set Q equal to 2. A new feature is seen in this Potts model example, however, neglecting for the moment the non-zero right-hand side, which can be eliminated by a suitable definition of G. We notice that when Q is greater than 2, there is no longer an order-by-order cancellation of the partial generating functions, but rather cancellation of combinations of partial generating functions of different orders. We can overcome this by converting to a self-reciprocal form by defining a new generating function G primed, given in equation 12, and then we have an inversion relation of the usual form, G primed xy plus G prime minus x1 over y is equal to right-hand side. So in general, our thesis is that the inversion relation and symmetry, plus some assumptions on analyticity, are sometimes sufficient to determine solutions completely. And in order to compute the generating function term by term, it's necessary, but not sufficient, to have some property relating terms of different orders. For our purposes, at least in this talk and in most of the successes of this approach, this property will be XY symmetry. We're going to look at some polygon models that display XY symmetry, including Ferrer's polygons, staircase polygons, directed convex polygons, three-choice polygons, and staircase polygons with a staircase hole. And we'll show that for the first four classes, the inversion relation provides sufficient additional information to compute the solution, whereas in the latter two cases, that doesn't. So here's the general framework. The general form of the generating function is g of xy is h1y x plus h2y x squared plus h3y x cubed, etc., where these partial generating functions hmy are rational functions with dm0 equal to 1. And the general form of the inversion relation is as shown here, gxy plus or minus y to the alpha, g of epsilon xy 1 over y, where epsilon is plus or minus 1, is equal to a right-hand side, often 0. Alpha is an integer, and as I say, the right-hand side is 0 usually, or some simple function. Writing the generating function g in this way is equivalent to writing these partial generating functions h in the form hm of 1 over y plus or minus epsilon to the m, y to the m minus alpha, hmy is equal to the right-hand side. That is to say, you can work in the framework of the generating function or in the framework of these partial generating functions. Now, whether the inversion relation is sufficient to compute the generating function is going to depend on the value of that exponent alpha and on the degree of the denominator's dm. Direct proof of the denominator form can often be obtained. So, for example, Faro graphs, it's easy to show that the denominator takes the simple form 1 minus y to the m, and while for staircase polygons, the denominator is 1 minus y to the 2m minus 1, just as we saw for the free energy of the Ising model. This is also true for directed convex and convex polygons. For three-choice and staircase polygons with a staircase hole, the situation is much more complicated, and the denominators take this form where you have two different results for m even and m odd. So we're going to assume that in general we know the denominator form either empirically or by rigorous proof, and that that denominator is of degree d subscript m. Now we're going to proceed inductively following what Rodney did for the Ising model. If we've already computed the coefficients h1 to hm minus 1 in that expansion, and if xy symmetry holds, then we also know the coefficients up to y to the m minus 1 in the expansion of the generating function. In particular, we can compute those same coefficients in the numerator polynomial p of the partial generating function. In order to obtain the unknown coefficients, we must be able to express them in terms of the known ones by means of the inversion relation. So if we write this polynomial p as aky to the k and use this expression for the inversion relation that d1 over y is plus minus y to the minus dm dy, then the inversion relation fixes the value of the combinations of these coefficients ak plus or minus al with k plus l equal to alpha plus dm minus m. And one can see, if one plays around a little bit, that one can then determine all the coefficients if dm, the degree of that polynomial, is less than 3m minus alpha. So this puts a constraint on alpha. So much for the general theory. We'll now look at some particular polygon models on the square lattice. A connected, just some quick definitions, which will be familiar to everybody, but I'll run through them. A connected sequence of steps we call a path or a walk. If no site on the path occurs more than once, the path is self-avoiding. If a path returns to its starting site in the final step and otherwise doesn't intersect itself, the result is a self-avoiding polygon. The number of steps taken is the perimeter of the polygon. the number of steps taken in the vertical direction is the vertical perimeter. Similarly for the horizontal perimeter, and the area is just the number of cells of the lattice enclosed by the polygon. And here are the particular types of polygon we'll be looking at: Ferrer's graphs, stack polygons, which can be oriented either vertically, as shown here, or horizontally; staircase polygons, where the bottom and the top paths are staircases; directed convex polygons, which is convex, which means that the perimeter is equal to the perimeter of the minimum bounding rectangle. But if you can see that there's a direction here, or just an arbitrary convex polygon, as in the case shown here. Then so a couple of examples. The area generating function for staircase polygons of width 4 is given by this rational function, and the partial generating functions satisfy this nice inversion relation. H1 over Q is equal to minus HQ. So it's self-reciprocal, and observe that the numerator here is not only self-reciprocal, is not only symmetric due to the self-reciprocity, but it's also unimodal, which is another nice feature. As another example, the semi-vertical perimeter and area generating function for column convex polygons of width 3 is given by this rather messy function, and it too satisfies a nice self-reciprocal expression for the partial generating function. Again, observe the symmetry of the coefficients: 1, 4, 2, 1, minus 1, 1, 4, 2, 1, minus 1, etc. So this is the sort of theorem, if you like. Here, N with an overbar and S with an overbar refer to the number of north and south steps in the upper part of the polygon, and N underscore S underscore is the number of north and south steps in the lower part of the polygon, and Y upper bar, Z upper bar, Y lower bar, Z lower bar are the corresponding fugacities or dummy variables corresponding to those steps. The width is M, so we don't have to worry about horizontal steps. This is just the function of the vertical steps. And the result is that if P is one of the systems we're looking at, Ferrer diagrams, stacks, staircase polygons, bar graphs, column convex polygons, then if we let P subscript M be the subsets of P containing all polygons of width M, and Fm the generating function, then Fm is a rational function and it is self-reciprocal. That is, F 1 over Y bar 1 over Z 1 over Y under bar 1 over Z under bar is equal to this, where C is a multiplier that depends on the particular problem. So and we have explicit representations for C in each case. So for example, it's minus 1 to the N over Y naught over bar YM under bar for bar graphs. And the proof of this uses Temperley's methodology. A more complicated methodology that's required in some cases is due to Stanley. Stanley has analyzed where the situation where the objects to be counted correspond to integer solutions of a system of linear equations with integer coefficients, that is to say, a linear Diophantine system, subject to a set of constraints. He's established certain conditions under which the solution to a given problem will be self-reciprocal. So to see how this works, if we consider the linear homogeneous Diophantine system psi of alpha equals 0 in the unknowns alpha 1 to alpha s with psi an integer matrix with P rows and S columns, and 0 a P tuple of zeros, then firstly the corank kappa is just S minus the rank of psi, and for a linearly independent system, kappa is just S minus P, where P is our P tuple of zeros here. Then if we let S be a set of integer solutions, the generating function Sy is the formal power series y to the alpha summed over all values S, where y1 to ys is just a vector of fugacities associated with the unknowns in this linear Diophantine system. So in our applications, we find two types of constraints on the unknowns, alpha j. Some are required to be strictly positive, others only are required to be non-negative. And conveniently, it's precisely these kinds of constraints that have been treated by Stanley. If we let the unknowns be alpha, which I define, which depend on gamma and delta in this way, where gamma is an n tuple, delta is an s minus n tuple, and likewise we let y be uv, then the notation in what follows the notation delta greater than 0 means that all the coordinates of delta are positive. Then the theorem of Stanley is that if E is the set of integer solutions to a linear homogeneous Diophantine system of corank kappa, such that gamma is greater than or equal to 0, delta is greater than 0, and then E bar is the set of solutions to the same system with gamma strictly greater than 0 and delta greater than or equal to 0. The system has integer solutions such that gamma is greater than 0 and now delta is less than 0, then EUV and E bar UV are rational functions obeying this reciprocity relation. And a sufficient condition that this function is self-reciprocal is that the linear homogeneous Diophantine system has the solution gamma delta is 1 minus 1. And in that case, we get the result that E of 1 over U, 1 over V is minus 1 to the kappa EUV, where this gives us our prefactor function that we saw in the previous examples. Stanley has also developed a more comprehensive theory, which gives correction terms for systems in which self-reciprocity fails to hold, but we haven't explored the ramifications of this theory. But we did need all this machinery to study staircase polygons with a staircase hole and for three-choice polygons. In each of these classes, the anisotropic perimeter and area generating function takes that general form, and then using these methods, we calculated the inversion relations for all the polygon classes mentioned above, and these, combined with XY symmetry, allowed us to solve these problems in the same way that Rodney Baxter solved the two-dimensional Ising model. And in the following two slides, I just show you the situation. So Ferrer's stack, staircase, directed, convex, convex. We find these self-reciprocity relations, which correspond to these inversion relations. Q here on the right-hand side refers to the area, and you'll see these factors, which are quadratic here. We can only handle the case where m is equal to 1, and then we get these inversion relations on the right-hand side. And there are further results for bar graph polygons, for directed column convex polygons, for column convex, for three choice, and then for staircase polygons with a staircase hole, where we get a very messy self-reciprocal relation, but the partial generating functions are tractable. So in summary, each method has its own particular uses for obtaining reciprocity or inversion relations. For example, the methods of Stroganoff and Baxter are suitable for lattice models in statistical mechanics characterized by a family of commuting transfer matrices. The Temperley methodology is mainly applicable to families of polygons that are column convex or nearly so. Stanley's method for obtaining reciprocity results applies to any problem defined by a system of linear homogeneous Diophantine equations, but the solutions to this system must be constrained by a system of simple inequalities of a certain form. It's probable that many lattice models in statistical mechanics can be framed as a linear homogeneous Diophantine system. However, most are likely to require more general types of constraints than the simple inequalities of the directed polyomino problems that we have considered. Likewise, the non-directed non-directed polygon problems that we've successfully treated using the Temperley methodology can be recast as linear homogeneous Diophantine systems with more complex constraints. We haven't searched for inversion relations for any polyomino problem in variables other than the natural variables for the problem, yet the example of the Potts model demonstrates that such inversion relations may exist. It's also possible that other symmetries can be found for some problems. And in conclusion, we suggest that, as Baxter has shown for the Ising model, the search for inversion and symmetry relation provides a powerful method to tackle certain combinatorial problems, which is yet another of the very many legacies that Rodney Baxter has left us with. Thank you very much.
Thanks very much for your talk, Tony. Do you have any questions? Andreas from Bar.
I have a question about the status of the inversion relation by Meyer and Jekyll. Can we understand this as an inversion relation that can be solved? That you have analyticity on the self-view line, and then you can solve the inversion identity. But away from the self-view line, it's more or less a duality transform. For the Q-sets Potts model, you have the inversion identity, a general inversion identity.
Certainly, in general, that's the same with S-matrix theory. You're combining the inversion relation with the crossing in that case, just the exchange of the two Guttmann constants, horizontal and vertical. You get naturally absolute function on your infinite product form. In the case of Stroganoff integral models and so on, this minimal solution is a good one.
Okay.
Yeah. For the Potts model, when you're
Thank you, Jean-Marie.
I have a question.
Vladimir has a question as well.
Yes, so my question is, so the Ising model has interpretation of enumeration of some polygons, self-intersecting polygons. And the other combinatorial problem you mentioned, do they have transfer matrix or formulation? So you can reduce the inversion relation for transfer matrix like it is done by Baxter and Stroganoff.
Sorry, can say that? Can you say that again?
The enumeration of polygons you mentioned.
Yes.
Do they have transfer matrix formulation?
You can set these things up in terms of transfer matrices, but that doesn't seem to be the most natural way of doing it. And everything that I've spoken about, we haven't needed to write down the transfer matrix explicitly, but you can certainly do so.
Jean-Marie?
Yeah, instead of answering questions, I should ask one. What you mentioned on the two-dimensional Ising model with your equation 8, 9, 10 can be done for the cubic Ising
Yes.
model.
Yes, indeed.
And again, we have this question, okay, what do we have at denominator? In fact, one discovers that one has other singularities than
Yes, exactly.
ends fruit of popping out. So, okay, too bad for the three-dimensional. We were close to solve the three-dimensional Ising model, but it doesn't. You have an idea of some three-dimensional problems that could be solved like that, for which the denominator are okay, and we don't have a proliferation of singularities?
The only three-dimensional model that I believe can be solved in this way is the three-dimensional generalization of convex polygons, which Mireille Bousquet-Melou and I solved by other methods, which is one of the very few exactly solvable three-dimensional problems, and that can be solved by this method also. But if you try and look at, say, the free energy of the three-dimensional Ising model, you get exactly the same situation as you find for the susceptibility of the two-dimensional model, in that you get these denominators zeros in the partial generating functions that fill the unit circle, which is my hallmark of unsolvability.
But you don't think that generating functions like lattice green functions will be a well-suited framework for that?
Well, that is Green's functions. I haven't thought of looking at those with that approach. Maybe when you visit next week, we can discuss that.
Yeah, okay. No, because at the end of the day, you know you're a winner. Lattice green functions are diagonal of rational functions.
Yes, I know that's your mantra.
Yeah.
Okay, then, on that note, let's thank Tony again for his time.
Thanks, Murray. Thank you.